In this video, we are going to see the polar plots for different functions which we have discussed in detail in the previous videos. In this video, we're going to see in brief what all we have discussed in the previous videos. Essentially, we're going to write the equation and show the plot and important points on it and important frequency equations and magnitude equations. And this video will be well suited for people who are looking for a revision kind of a thing or a quick review or quick recap. Okay, so to start with, we'll start with the function. Okay, uh, 0 at the origin, and the plot for this on a complex plane looks like this. Okay, it starts at 0, the origin on the complex plane. Okay, this is real value, this is imaginary value, and as omega tends from 0 to infinity, the plot looks like this. Okay, it goes on increasing and goes towards infinity. This point is corresponding to omega equals to 0, and this point is corresponding to omega tending to infinity. As we substitute s with j omega, this equation becomes j omega, and as we vary omega from 0 to infinity, we get these values. Okay, this is how the plot looks for 0 at origin. And if you look for pole at origin, and if you substitute s with j omega, the equation becomes like this. And if you look at the polar plot for this particular function, when omega equals to 0, it is infinity. Okay, 1 by j, we can write minus j in the numerator, and it starts from minus infinity on this imaginary axis and tends to 0 as omega tends to infinity. Okay, this point is corresponding to omega tends to infinity, and this point will be corresponding to omega equals 0 where it tends to infinity. Okay, and if you look at simple 0, okay, which is 1 plus st form, if you look at the polar plot for this magnitude will be 1 in this case. Okay, and the plot looks like this. Okay, only the imaginary value will be changing, and it will be tending to infinity, and the real value will be constant all the time. As we can see from the equation, if you substitute s equals j omega, we see how it is going to change. Okay, and this value is corresponding to omega equals 0, and as this goes to infinity, it is omega tends to infinity. Okay, and if you look at a simple pole, which is 1 over 1 plus st, if you look for this and plot this equation, which we have already done for all of these, okay, it looks like this, and this point is corresponding to omega equals to 0, and this point is corresponding to omega tending to infinity, and the arrow mark directions are this way, which indicates that this is in the direction of omega increasing. Okay, and we have seen certain points where the maximum value of this on the imaginary axis, okay, will happen when the phase angle is minus 45 degrees, and the magnitude of this, okay, this point will be 1 by 2, and if you look at in the real axis, it will be 1 by 2, and if you recollect, this magnitude will be 1 when omega equals to 0. And if you look at this phasor which we are plotting here, the magnitude of that will be 1 divided by square root 2. Okay, this is how the plot for a simple pole looks. If you plot for two simple poles, which is 1 divided by 1 plus st1 times 1 plus st2, the polar plot for this equation looks like this. It starts at a point where it is magnitude is 1, okay, and it ends at a point where this is when omega tends to infinity, and this is this point. Okay, omega equals 0. Fine. And this plot looks something like this. Okay, and the arrow mark directions are in this way. And the important points are, what is the frequency at which this polar plot is going to touch this negative j omega axis, where the phase angle is minus 90 degrees. If you substitute this in the 5 equation, we'll get the value which is this omega equals 1 over square root of t1 t2. And if you look at the magnitude, okay, from here to here, this point, if you take this value, okay, I'm writing it here, it will be square root of t1 t2 over t1 plus t2. This is how the plot for a two simple poles looks. Okay, if we take a transfer function with three simple poles, okay, which is 1 over 1 plus st1 times 1 plus st2 times 1 plus st3. If you plot the polar plot for this function, okay, when omega equals 0, the magnitude will be 1 and the phase angle will be 0, which we have already seen. Okay, this is corresponding to omega equals to 0. And when omega equals to infinity, we'll have a point, okay, the magnitude will be 0 and the phase angle is minus 270, because we have three poles, okay, three simple poles. And the plot looks like this. Okay, and as omega is changing from 0 to infinity in this direction, okay, we indicate the arrow marks in this way. Okay, this point is corresponding, this point, okay, is corresponding to omega tends to infinity, or omega equals infinity. Now the point is, okay, what is the omega at this particular point when the polar plot is touching minus 90 degrees? This line is corresponding to minus 90 degrees, and this omega will be equal to 1 over square root of t1 t2 plus t2 t3 plus t1 t3. Okay, and if you look at the polar plot when it is crossing minus 180 degrees or 180 degrees, you can say, because if you measure in the anti-clockwise direction, it is 180 degrees. If you measure it in the clockwise direction, it is minus 180 degrees for the same point. Okay, so the omega for this particular value, if you write down, this will be square root of t1 plus t2 plus t3 whole divided by t1 t2 t3. Okay, this is how the plot looks for this. And we are not concerned about the magnitudes here because the equations become really lengthy and it's not actually worth remembering them. Okay, we will see situations where when we are looking for the stability of a system by using Nyquist stability criterion, we need to usually look for the magnitude when it is crossing the 180 degrees line, okay, which is negative real axis. That is the reason why if you just know the frequency at which it crosses, we can easily calculate the magnitude and say whether it is encircling minus 1 or not, and say whether the system is stable or not. And we use these concepts even in calculating gain margin and phase margin. We'll come across this later in the videos. Okay. Now, if you see a transfer function with a pole at the origin and one simple pole, okay, and for this, if you substitute as with j omega and if you plot this, okay, the plot looks something like this. Okay, oops, let me redraw this. It goes like this. Okay, this is the arrow mark directions, which is indicating this point is when omega equals 0, this point is when omega tends to infinity. And if you look at this point, is minus t1, and we can represent this is t1. This is the distance of this point from the origin. Okay, real axis and imaginary axis. And if you look at a transfer function which is having a pole at the origin and two simple poles or two non-zero poles, then if you plot for this a polar plot, we'll have a function, okay, a plot which looks like this, okay, t1 plus t2, and this point will be minus of t1 plus t2. This plot looks like this and tends to this as omega. This is actually starting from here, okay, this is when omega equals to 0, and this point when it is 0, this is when omega tends to infinity. And the arrow mark directions are this way because the omega is increasing in this direction. And we would like to know what is the frequency at which this polar plot is crossing this minus 180 degrees. And if you look at this omega is 1 over square root of t1 t2. If you look at the magnitude at this point, okay, this magnitude I am talking about, at which this polar plot is going to cross this 180 degrees, we know the frequency of that, and if you substitute that back in the equation, we'll know the magnitude of this. And this magnitude will be t1 t2 over t1 plus t2, okay. And if we look at another function which we have discussed in the previous videos, okay, 1 over s times 1 plus st1 times 1 plus st2 times 1 plus st3, okay. If you take polar plot for this, the polar plot for this looks, let's draw for this point, the reference we are taking will be minus of t1 plus t2 plus t3, and when omega equals to 0, the real value will be minus of t1 plus t2 plus t3, and imaginary value will be infinity. If you take reference, okay, it's going to start from here, and when omega tending to infinity, the phase value will be 360 degrees, okay, actually minus 360 degrees, which is 0 degrees if you measure in the anti-clockwise direction. And the point will be here, and the plot looks like this. Okay, and the arrow marks will be in this direction, as this is in the way as omega equals to 0 here, and at this point omega is tending to infinity. And we would be interested in the frequencies at which this plot is crossing this minus 180 degrees. This frequency, this is minus 180 degrees, okay, and the frequency at which this is crossing minus 270 degrees, which is, we write minus 270 degrees, okay. Let's write these equations, okay, and this equation, which is omega minus 180 degrees, will be equal to 1 over square root of t1 t2 plus t2 t3 plus t1 t3, okay, and omega minus 270 degrees will be equal to square root of t1 plus t2 plus t3 whole divided by t1 t2 t3, okay. These are the two values, and we are not concerned about the magnitude because it will be really complicated in terms of equations. But if we know these values, when a real problem is given, we can calculate this by using these equations directly and use this frequency and or the angular frequency, substitute back in the equation and get the magnitude value, which will be easy. Okay, and we have discussed so far, okay, these equations, okay, and let's see for these plots which have j omega or a pole at the origin have a magnitude at 0, okay, omega equals to 0 is tending to infinity, whereas the magnitudes for these plots which have only simple poles in their equation will be at 1. In the next coming videos, we will see some small tips by which we can actually, instead of actually going and analyzing it in detail by using equations, just by looking at the equation, we can plot the polar plot with intuition, okay, by knowing only few plots from all these plots which we have discussed, okay.